Hi everyone, my name is Ningyu from Peking University. Today I will give a presentation of our work, USENIX security analysis of USIO smart contracts. First, I will talk about our work's motivation. USIO is the first well-known blockchain that adopts DPoS as consensus algorithm. The DPoS can make the TPS of USIO tens or even hundreds times of Ethereum and Bitcoins. Besides, the highest market cap of USIO has reached up to nearly $18 billion in April 2018, and the second peak, as the red arrow illustrates, also reached nearly $14 billion in this month. The app ecosystem was extremely active. Only 3 months after its launch, the daily DApp users and transaction volume has surpassed the Ethereum's, which is one of the most famous platforms that supports DApp. Therefore, such a high-value platform would definitely attract malicious users to hack money in smart contracts. For example, in December 2018, US Bad Eyes was suffered an attack against rollback vulnerability. This leads to nearly 200,000 US tokens financial loss. According to our dataset, there have been more than 100 times of attacks against types of vulnerabilities which are resulted from developers of smart contracts or USIO's design flaws. In Ethereum, the vulnerabilities and attacks also exist. However, there are dozens of tools that are used to detect types of vulnerabilities in Ethereum smart contracts. For example, some representative work like Authorize, Securify, Tether adopts kinds of programming analysis methods to analyze Ethereum smart contracts. However, in USIO, prior to our work, the automated vulnerability scanner is much more or less. There are few well-known tools yet. Next, we will briefly introduce some background information of USIO smart contract. This smart contract is written in C++ and compiled into WebAssembly bytecode. The figure on the right side depicts a specific function named apply. This function is a dispatcher handling the received invocation and notification. The signature of apply is fixed. It takes 3 arguments, receiver, code, and action, respectively, corresponding to the recipient name, the count in which the code is executed, and the name of targeted function. Therefore, transferring US token is a little different with Ethereum. The upper part is a normal situation. First, the user has to invoke the transfer function in USIO.token to make a request to transfer money to the app. Once the official account updates the balances of the initiator and the recipient, it will notify both of them. Last, as a notification is initiated in transfer function, the apply will dispatch a notification to the DApp's transfer function. Note that all the code fields in first 3 steps stay unchanged, as the notification will not change the code. However, the lower part shows an attack against a fake US vulnerability. Specifically, malicious user would transfer fake US token through another account, like US.token1. This US token is worthless, but the notification is initiated in the transfer function. It can also be dispatched to the recipient's transfer function. We call this kind of vulnerability as fake US vulnerability. Except for the fake US, we also focused on 3 other vulnerabilities: fake receipt, rollback, and missing permission check. All these 4 vulnerabilities are commonly emerged in the interaction between users and the apps. Therefore, implementing a framework to detect the vulnerabilities in USIO smart contract is necessary and urgent. We decided to use symbolic execution to recover semantic information to automatically identify if the current smart contract is vulnerable to any of these 4 types of vulnerabilities. However, there are mainly 2 challenges. First, existing tools on detecting vulnerabilities in Ethereum smart contracts cannot be directly adopted in detecting vulnerabilities in USIO smart contracts. This is because the WebAssembly bytecode is much more complicated than the Ethereum smart contracts. The complexity does not rely on reflex on the amount and the variety of instructions, but also on the control flow, which often contains multi-level nested loops, and the vulnerabilities heavily rely on semantic information to be verified. Secondly, the symbolic execution has some inherent challenges, including memory modeling, external dependency, and path explosion. Specifically, if the address is a symbol, how to effectively and precisely retrieve and store data. Moreover, the source code, even the bytecode of the library function, cannot be obtained. How to emulate this function's behavior? Last, the path explosion can significantly consume the resources and increase the analyzing time, especially when encountering the multi-level nested loops. Thus, how to address these two challenges are mainly focused by our framework. We designed and implemented EOSAFE, a tool to automatically detect mentioned 4 types of vulnerabilities in USIO smart contract. EOSAFE is composed of 3 key components: WebAssembly symbolic execution engine, EOSIO library emulator, and the vulnerability scanner. It takes the pre-processed smart contract as input and generates a report by symbolically executes this contract. Next, we will briefly introduce these 3 components. First, the most important component is the symbolic execution engine. We implemented all 172 instructions with the help of BitVector in these 3. Also, during the symbolic execution, it traverses all the possible paths. Each feasible path corresponds to a state, maintaining the date structure in WebAssembly bytecode. To address the path explosion problem, we export 2 options, timeout and DApps, to limit the analyzing time and the depth of call stack. Experiments show that this heuristic approach is simple but efficient. Also, to address memory modeling problem, we adopt a mapping structure to mimic the memory area to obtain a precise and efficient result. But this structure will import memory overlap problem, and the figure shows. Thus, we also propose a formally verified memory merging algorithm to address this problem. And we also try to address the external dependency issue. To be specific, after manually checking the contracts in our benchmark, we filtered out commonly used library functions. Then, according to their functionality, we divided them into 5 categories, as the right figure shows. Due to a lack of their implementation in bytecode format, we modeled their behavior according to their release source code in its official repo. Moreover, if an external function is not modeled during the symbolic execution, we use the symbols to balance the stack to continue the analysis. Last, we implemented a scanner which consists of 2 steps, locating suspicious functions and detecting vulnerability. Therefore, the scanner can firstly use heuristic strategies to locate the possible vulnerable function. Then our tool will symbolically execute that function and record all its feasible paths. With the help of each path constraints, the tool could identify if the contract is vulnerable to a certain type of vulnerability. For example, the right formula explains the way of how we prove the existence of fake US vulnerability. The implementation of scanner reflects good scalability, which enables other researchers to extend our work and achieve their own detectors. As we mentioned before, we constructed a benchmark to evaluate the performance of EOSAFE. To be specific, we built the benchmark by collecting official announcements, cryptocurrency forums, and technical articles and blogs. The benchmark consists of 52 contracts. We have conducted manual recheck to avoid the attack was due to other factors rather than code flaws in smart contracts. Moreover, we have released the benchmark in my repo on GitHub. The evaluation result illustrates that EOSAFE did a good job on detecting vulnerabilities, reaching up to more than 98% F1 score. Also, we compared EOSAFE with the traditional symbolic execution tool CLI by converting WebAssembly bytecode to C code. The results show that EOSAFE outperforms significantly, and the CLI solution has some drawbacks. After proving the performance of EOSAFE, we evaluated it on our dataset, which includes all the contracts deployed before mid-November 2019, more than 53,000 versions of 5,000 contracts. A contract corresponding to multiple versions here is due to the contract in USIO is updatable. We collected all their versions. Here are some interesting results. Nearly half of smart contracts were once vulnerable to at least one kind of vulnerability. Fake receipt is the most widespread one. As for the affected versions, missing permission check vulnerability impacts more than others. With the vulnerable versions of contracts, we can further evaluate how long it will take to fix vulnerable in USIO smart contracts. On average, patching a vulnerability requires more than 2 weeks. Moreover, as the rollback vulnerabilities only appeared in gambling smart contracts, it is patched most timely. What's more, by analyzing if the latest version is vulnerable, we figured out more than 3/4 of smart contracts were still vulnerable, especially the fake receipt vulnerability. We have also performed other interesting evaluations, which are detailed in our paper. Finally, here are some takeaway messages for you guys. We proposed the first symbolic execution engine for WebAssembly native code. Based on the engine, we implemented an accurate and scalable framework, EOSAFE, which outperforms the CLI solution on detecting vulnerabilities in EOSIO smart contracts. Also, we constructed and released a manually rechecked benchmark. Evaluation on the benchmark illustrates promising performance on EOSAFE. Last, we applied EOSAFE on over 53,000 smart contracts, which reveals serious security issues in the ecosystem. At last, I would like to express my appreciation to my co-authors, anonymous reviewers, and you guys. If you have any following question, please contact me by this email. Thank you.